So today in this video we'll be studying about the levers. So levers are the simplest type of machines. A lever is a rigid bar, either straight or curved, that can rotate around a fixed point known as fulcrum. It is also shown here in the picture. This point F is the fulcrum. Effort E is applied at one point on the lever, which is being applied at point P, located at a certain distance from the fulcrum, while the load to be lifted or moved acts at another point, also at a specific distance from the fulcrum. In this picture, we can clearly see that at point A, load is being attached. The perpendicular distance from the load to fulcrum, so from point A to point F, is known as the load arm, while the distance between the effort to the fulcrum corresponds to the effort arm. Next is the principle of lever. A lever operates based on the principle of moments. For an ideal lever, which is assumed to be weightless and frictionless, equilibrium is achieved when the net moment about the fulcrum equals to 0. This condition is met when the moment of the load and the moment of effort around the fulcrum are equal in magnitude but opposite in direction. So, in equilibrium state, what we can say that load into load arm, which is the AF, and effort into effort arm, which is BF, are equal. The product of them is equal. Now we know that the mechanical advantage is the ratio of load to the effort, which is equal to length of effort arm to that of length of load arm. This is equal to P by A. Here L is the load, E is the effort, AF is the load arm, while BF is the effort arm. Mechanical advantage of lever is derived from the principle which is equal to load by effort, which is equal to length of arm AF upon length of arm BF, which is equal to B by A. The mechanical advantage of an ideal lever is equal to the ratio of the length of the effort arm to that of the load arm. Next is the kinds of levers. So based on the relative position of the load, effort and fulcrum, levers are categorized into three classes. Class 1 levers. In class 1 levers, the fulcrum is positioned between the load and the effort as shown in the figure. In this type of lever, both the load and the effort act in the same direction, in downward direction in this picture. For class 1 levers, the mechanical advantage and velocity ratio can vary. They may be greater than 1, equal to 1 or less than 1. The mechanical advantage of a class 1 lever depends on the relative lengths of the effort arm and the load arm. The first case is that mechanical advantage is greater than 1. If the effort arm is longer than the load arm, the lever provides a mechanical advantage greater than 1, because we know that mechanical advantage is the ratio of length of the effort arm to that of the load arm, right? So if the effort arm is longer than that of load arm, definitely the mechanical advantage will be greater than 1. Examples are pliers, crowbars, and the handles of water pumps. Number 2 is that mechanical advantage is equal to 1, and this condition will be met when effort arm and load arm are of equal length. In that case, mechanical advantage will be 1, as seen in a beam balance or a physical balance. Last is the mechanical advantage less than 1. When effort arm is shorter than the load arm, the mechanical advantage is lesser than 1. Examples are scissors and oars used in rowing a boat. Now, some of the examples of class 1 lever include the devices like a seesaw, pliers, shears, scissors, crowbar, claw hammer, hand pump handles, oars, spades, beam balances, physical balances, and some of them are also shown here in the picture. A real life example is the nodding of the human head, which also functions as a class 1 lever. Next is the class 2 lever. In class 2 levers, the load is positioned between the fulcrum and the effort. The fulcrum is located at one end of the lever while the effort is applied at the opposite end, which is shown in the figure. Now, in this particular case, the effort arm is always longer than the load arm. We can also see that in the picture here. The fulcrum is still in between the load and the effort. Actually, we can't say in between, exactly in between. It is positioned somewhere in the path, in the line that joins A and B. However, the effort arm is longer than that of the load arm. This ensures that the mechanical advantage and the velocity ratio are always greater than 1, because mechanical advantage is the ratio of B by A. Since B is longer than A, then definitely this value will be greater than 1. The key feature of class 2 levers: they always function as a force multiplier, making it easier to lift or move heavy loads with relatively little effort. Some of the examples of class 2 levers are nutcrackers, bottle openers, which are also shown here in the picture. The doors and car jacks are some of the other examples. This topic is clear to you? Thank you.